Hello dear students, I am Professor Nadeemur Rahman at Department of Mathematics, Aligarh Muslim University, Aligarh. I will teach you a course of a group theory over 12 weeks. So let us start. In the first lecture we have to start with the binary operations and all these things. Let's begin with binary operations. So we start with the binary operation means we have take a set of integers z cross z. We take some two integers as the elements of this is like this. M and n are the two ordered pair from z cross z to z, and you can see this if we take a sum of this m plus n, this is again is a set of integers, and this give you a unique integers in this set is this. So in certain way we can say that if we have a take addition as a mapping from z cross z to z, then we have to get a unique elements. In this case, if m and r, the sum of these two integers is giving you a unique integer. So in this case we have to define is a binary operation is this form. Let for every ordered pairs of integer m and n, their associate is a unique integer m plus n, and we can say that we may therefore think of addition as a mapping from z cross z into where the image of a z mn belong to the z cross z is denoted by m plus n is there. Let us define with the formal definition of a binary operation is there. Let S be a set. A binary operation on S is a function from star S cross S to S. Then we have to just say that this A, B are the ordered pair of a S cross S, and we have to map A star times A, B is equal to, generally we have to denote it as this A star B from the set S cross S of a ordered pair of elements S into S is there. So we can say simply is this the image of this S cross A cross B belongs to the S cross S under the operation S. We generally denote it as a star B is this thing. So let us try to describe this definition a little. First of all, binary means simply indicates that operation takes two elements of S and split out a new elements of elements there. As also we have written a star as a function from S cross S to S, which means there is a two things under is there. First is the operation star is a well defined. Well defined means we have a and B are the element of a S. There is a exactly unique C belongs to the S such that A star B is equal to C. In other words, the operation is defined for all order pairs, and there is no ambiguity in meaning of A star B is there. Second thing is that this S is a closed under the star for all A and B belongs to the S, then A star B is again is in S. So we have to two things when we have to keep in mind showing that the set is a binary operations. One is the well definedness, we have to the set is a well defined. Another is we have to just say that is a this set is a close is there. Let us begin with the definition of this. Addition and multiplications of set of integers and set of rational number and set of real numbers, or we have to take a set of complex numbers, are the examples of a binary operation. For example, if we take any two x and y are the elements of a set of integer, then addition we have to taking map. So this means addition is z cross z to z is mapping we define. If we x and y are the element of a z, then clearly x plus y is giving a unique integer and which is also belong to the z, means is a well defined and the close is there. So this means this is a clearly under addition is a binary operation. Also if we take x and y are the elements of a z, if we have to prove that x into y, then the product of a two integer is again is an integer, that means is again is a belong to the z. So x and y are the two integers, then the addition, and so we simply say that x this set of integers under addition and multiplication is an example of a binary operation. Similarly, we take as for a Q and R, this is also the another examples of a binary operation. Let us define another example. We have to just take a addition and multiplication of m and n, all m I and n by n matrices over the real numbers are the binary operation is there. Let us try this. Means we have to just take a very simple case. If n is equal to 2, we take a 2 by 2 matrices like this. We take A is equal to any two matrix A, B, C, D, and A, B, C, D are the elements of R, and B is also the it can be written in the form of another matrix. We have A1, B1, C1, and D1. Then easily we can see that A plus B, we can simply write that is equal to A plus A1, B plus B1, C plus C1, D plus D1. And then we know that A, B, C, D and A1, B1, C, D1 all are the elements of R, because we take this a set of real numbers. So this A plus A1, B plus B1, C plus C1, D plus D1, these are belongs to the set of real number. So this means this is clearly well defined, and this is under the closed, this is whole set is belongs to the M of 2 of R. So in generally we can say that a matrix under addition is closed and matrix under multiplication is also closed. We have to multiply it as any two real numbers, we have to get it again is a real number. So simply we say that and matrix addition and multiplication of any n by n matrices over the elements are real is a binary operation is there. Let us try different example is there. We have to take a set set is S is equal to 1 to 3, and we have to just say that A star B is equal to define in this form. So we try into this form. Suppose we have to take a 1 star 1, that is by the definition is equal to 1, and 1 star 2 is also 1, and 1 star 3 is also giving you the 1. So this is all this in all the cases this 1 is the element of this S. Suppose we take a 2 star 1, that is equal to 2, and 2 star 3 is also giving you have a 2, and simply we can say that 3 star 1 is equal to 3, and then we can say that 3 star 2 is also is equal to 3. So in all the cases we have to find that if we take a composition B of is equal to A is defined in this phase. So in this case all of them properties, this is saying that element of S, so this is well defined and it's giving the every time is a unique element you cannot find in this form, and also this is closed in the case of this thing. So satisfy both the conditions of a binary operations definitions. So clearly this S under this binary operation define a composition B is equal to A for all AB belongs to the S is a binary operation on the set of positive integers. So clearly this is we take, for example, if we take a 2 and 5 are the element of a Z star, then we have to take a 2 minus 5 is equal to minus 3. Minus 3 is clearly not is the belong to the Z star. So in this case we can say that the subtraction under of the set of a positive real number integers is not a close under this binary operation. So under addition this is not a close, that means clearly this is not a binary operation is there. Let us try another example. We have a different example. We take a define star on set of a real number is such a way A star B is equal to A divides B, and this operation is again is not a binary operation. It is not as a binary operation because if we take a B is equal to 0, so this is composition is not a well defined. So we can say simply is there since it is defined everywhere except B is equal to 0. So this means this map define A star B is equal to A divides B is not a binary operation in the case B is equal to 0 in case is there. If we change this little bit, if we take a star is defined as in place of a R, we take a set of a R star means we have all the elements except 0. So now we have to just see that this is defined everywhere. So for R, this map is defined is not a binary operation, but in place of R, we take a non-zero real numbers. That means except 0, this function is defined everywhere and closed everywhere. So we can say that is clearly this is a binary operation in this case of a star b is divided if a R is a non-zero real number is there. Other example is this: we have to look at a star b, we define is a star b is equal to c, and we have to put a restriction there. C is some large number than a plus b is there. So let us try this. Means on a real number we take a 2 and 3 are the real number. Then he said that 2 star 3 is equal to c, whereas c is what? C is nothing but is equal to is a greater than of 2 plus 3. 2 plus 3 is a 5. So that means c is maybe is a 6, 7, 8, 9 and so on, any value. So c can be, there is a c is a number is that is not a unique number, we have to fetch that. So a star b is not giving the unique is there. That means we can say that is not a well defined in this case. So it's not a well defined, since we just say that in this case you see we take any 2 plus 3 is equal to 5. 5 means is a larger than 5 is 6, 7, 8 and that is not produce a unique number. So in this case we can say that this is not a well defined, since it is not clear exactly a star b should be what exactly what a star should be is there. So in this case we can simply say that this map is not defined. So this is clearly we say a star b is equal to c, where c is a sum larger than a plus b is clearly is not a binary operation in this case. Let us try some another very interesting example is there. We define a set of binary operation of a Rn, and we take a star b is equal to a dot b ordinary dot product, and then this is not a binary operation. Why is not a binary operation? We can simply say that we take a two elements of Rn, and then we have to multiply, take a dot product of these two elements is there. Let's for example we take a R2 is there, A is equal to we have a 1 2 and B is equal to we take a 3 4 from R2, then A 1 2 dot 3 4 is simply is 1 into 3 plus 2 into 4 is equal to 3 plus 8 is equal to 11. So in this case we can simply say that this and this 11 and 11 you can see this is the belongs to the R, is a scalar quantity, is not belong to the Rn. So we can simply say that in this case this is not a closed, because this is not belongs to the R2. So in this case this map is defined Rn, and the binary operation we take a dot product is clearly is not an binary operation in this case is there. Let us try we take a special type, and we say the matrix of any matrix under addition and its multiplications over set of real numbers or n by n matrix is a binary operation. Now very interesting question is there: if we take a matrix which has a set of all n by n invertible matrices, a collection of a over the coefficients of a real number, then the map operation is addition. We have to thinking about the binary operation we taking as addition, and take all the invertible matrices are there. So if a invertible matrices are there, we clearly we take a is the element of a GLNR. This means A is a invertible matrix is there. If A is a invertible matrix is there, then clearly we say that minus A is also belongs to the GLNR. So this minus A is also is an invertible matrix is there. So we can simply say that if we take A plus minus A, we getting is a zero matrix, and you know that the zero matrix is not an invertible matrix. So this means 0 is clearly does not belongs to the GLNR. So we simply say that if we take in place of an ordinary matrix, we take a collection of all the invertible matrices n by n invertible matrix, then we simply say that A plus B is not an again is a invertible matrix. So this is not closed under the addition. So simply we say that this matrix set of all invertible matrix collection under addition is not an binary operation. But if we take this same matrix for a in the case of a under multiplications, so this is satisfy all the satisfy the condition of a binary operations, both the condition of a binary operations, if we take any two matrices A belongs to this, then the product of a two invertible matrices again is invertible. So this is clearly is, we can say that is a binary operation under the multiplication of a invertible matrices are there. For this example, we can say simply is this, we can say that the all invertible matrices are means the determinant of this matrix should be is not equal to 0. So we use the property of a determinant of A is equal to AB is equal to, we can write the determinant of A into determinant of a B, and you know that the determinant of A clearly is determinant of A is clearly is not equal to 0, because A belongs to the GL2 is invertible matrix. If it is invertible matrix, then determinant is not equal to 0. Similarly, in the case of a determinant of a B is also not equal to 0. If B is the this invertible matrix, then determinant is not equal to 0. So if the determinant of A and determinant is not equal to 0, that this quantity is clearly not equal to 0, this quantity is clearly not equal to 0. So this whole product is clearly, we can say that is not equal to 0. So this means we can say that determinant of AB is not equal to 0. So this implies that if we take a product of any two matrix A and B, that is also is a invertible matrix is there in this case. So we can say that simply this under GL and R under the binary operation multiplication is a binary operation, but under the operation of addition, this matrix, all invertible matrices are not a binary operation is there. So now let us move to the some other properties of a binary operations. You know that in the number system we have to starting from the first operation is associative. Let star be a binary operation on a set S. This means is a satisfy both the condition is a well-definedness and the closeness is there. Then we say that this operation is a associative. It is satisfied the A composition S over A star B over C is the same as A star B, A star over B star C for all, means this satisfy this condition, satisfy this condition for all A and B belongs to the S. In this case, we can say that is a associative. Similarly, we can say that a binary operation star is a binary, let star be a binary operation on a set S, then star is said to be a commutative if A star B is the same as a B star A for every A and B are the element of a S are there. For examples, we can just say that for these two, simply example is the usual addition, usual binary operation of addition and multiplication of set of integers, set of rational number and set of real numbers are commutative and associative both. For example, if we take x, y and z are the element of a set of integers, if we write x plus y plus z, and this is the same as, we can say that this is x plus y plus z is the same as a x plus y plus z. For example, if we take particulars as a 2, 3 and 5 are the element of an integer, that is 2 plus 3 5 can be written in the form of a 2 plus 8 is equal to 10. Other way we can say that this is 2 plus 3 plus 5 is equal to 5 plus 5 is equal to 10. So these two are the same. In this case, we can say that simply as a set of integers, set of real numbers, set of a rational number and addition and under multiplication, they are clearly is a binary operation. The binary operations are commutative and associative. Commutativity is very trivial when we have a x plus y is the same as a y plus x for every x and y are the element of a set of integers are there. So in this case, we can simply say that this is x and y are the, for all x and y are the element of a integers. So this is clearly, we can say that these are the trivial examples of a under addition and multiplication is a binary operation into this. Simply, we already proved that the matrix addition is a binary operation, and this is also, we can say that addition of two matrices is the same as we have to take addition if A and B. A is the matrix of M and R and B is also the element of a M and R, then A plus B is the same as a B plus A. It is trivial. This is, we can say, for example, we take any 2 by 2 matrix A, B, C, D and take a plus of A1, P1, C1 and D1, and then we have a sum is this A plus A1, B plus B1, C plus C1, D plus D1, and then you can see this can be written in the form of this because these are two these A1 are the element of R, B1 are the element of R, and real number under addition is a commutative. This can be written as A plus A1, B1 A plus A1 plus A, B1 plus B, and then C1 plus C and D1 plus D, and this can be further written in the form of we can say that is A1, B1, C1, D1 plus A, B, C, D, and then you can see this is clearly we have to write in the form of a this is B, so this is kind of B plus A. Similarly, we can easily show that this is a satisfy the associativity also is there. So matrix addition and this is associative and commutative, but matrix multiplication is clearly associative, but matrix multiplication is not commutative in both M and R, and the GL and R means we have all invertible matrices there. For example, we take a two matrices, A is equal to 1, 2, 3, 4, B is equal to we take a 0, 1, 1, 0, and then we have to take a product of these two matrices. Clearly this 2, 1, 4, 3 this matrix, and BA is equal to this. Then now you can clearly see these two matrices are different. You know that the matrices are equal if the corresponding elements are the same. So these two elements are the different. These two are the element of this, and these two are the element. All elements are the different. So this means these two matrices are not the same. So we can say that clearly AB is not equal to BA. So matrix multiplication, either we have to take any n by n matrix over the set of real number, or GL and R set of all invertible matrices over real number. They are associative under multiplication, but not commutative under this operation is there. Consider the set of operation of subtraction. We see that operation Z set of integers, and clearly this under subtraction is a binary operation because we have to take any two integers satisfy this condition, which is not associative and also not commutative. We take a 2, 3 and 7. These are the three integers. Then we take clearly 2 minus 3 is equal to you have a minus 1 is not equal to 3 minus 2 is equal to 1 is there. So clearly 2 minus 3 is minus 3 is not equal to into this form. This is not a commutative. Then again we have to just satisfy this condition. We have a 2 minus 3 minus 7, so this is equal to you have minus 1 minus 7 is equal to minus 8, and then you have a, so subtraction is under subtraction of a set of integer is neither associative nor commutative is this case. Suppose we take a cross product of this another example. We have to thinking about the cross product on R3, and that is clearly is a binary operation. This means it's combine two vector produce a new vector. If you multiply the two vectors and then we take a cross product over this is again is a vector quantity. So this produced another vector quantity. So in this case we can simply say that this is a binary operation, but this binary operation is neither commutative nor associative, because you know that in the standard property of a vectors, if we take A and B, A, B, C are the three vectors of R3, then A cross B cross C is never equal to A cross B cross over C. Also A cross B is equal to minus B cross A. So that means you can simply say that this cross product is a binary operation, but this cross product is not a associative and commutative condition satisfied into this form. Let us one more example we have to discuss. This is R be the set of integers satisfied binary operation. We take a different type of binary operation. A star B is equal to, we take A plus B star B. Then this clearly we can verify that this associative and commutative. Clearly we take A star B we can write in the form of a plus b plus ab is given this thing, because a and b are the set of all non-zero real numbers. So this can be written as a b set of non-zero number is a commutative. We can write a b plus a, and under multiplication is also commutative set of non-zero number. This can be written in this form, and this is nothing but is equal to, by the according to the definition, this is a b star a is there. So similarly we can prove that this set is commutative, and also this set is associative. We can easily see in this case this satisfies these two conditions. Okay. Now another example, we take a set of power set of a binary operation is union, power set, binary operation intersection, or associative. Clearly you know that if a power set is there, A and B are the member of a power set of any set S, then you take a intersection B is the same as a B intersection A, and also this property A intersection B intersection, if C is also belongs to the power set of S, C is the same as a intersection B intersection C is there. So it's also satisfy the conditions of a binary operation is under intersection and union is satisfy both the conditions of associativity and commutativity. This is clearly we have to so into this form is there. Another very example at this, let R be the our set, and let a binary operation defined by a cube plus b cube. Now if a cube b cube, clearly you can write the same as a b cube plus a cube. So this set is clearly visible as a commutative, but you can see this is, we can see as clearly is not an associative. Why it is not associative? We take a, b, c are the two real numbers. So a composition, b composition is equal to a composition. B composition according to definition is b cube plus c cube, and then we have to apply a composition of this, then a cube plus b cube plus c cube ka whole cube. And another way we have to calculate in this form of this, a star b star c is equal to a cube plus b cube star c, and then again we a cube b cube ka plus b cube ka whole cube and plus c cube is there. So clearly it is mentioned that a composition b composition c is not equal to a composition b composition c. So clearly this binary operation is defined is not an associative. So we have to discuss this first lecture, it's a binary operations, and then we have to just take a two basic properties of a binary operations. We say that is a when these two binary operations are associative and commutative condition is hold, and we will discuss various examples of these binary operations are clearly. So now I just I have to stop for this first lecture. We have to continue in the second lectures by the some other properties of this, and when we start from the our lecture with the algebraic structures, and then define some algebraic structure, all this. Thank you very much for this first lecture.